Okay, so in this video I'm going over certain questions from the review worksheet to help you prepare for the test. Number 5, right? The equation used for a bank account that is earning interest, which is being compounded n times a year. So this formula will be given to you. A equals P times 1 plus R over N to the NT. Again, the key word is if you see the word compounding interest. Okay, so it'll be provided to you. There's another formula, right? Compounded continuously. Again, this will also be given on the test if you see A equals P e to the RT. So if you see the word continuously, compounded continuously, this is a formula you will use. If you see the word compounded quarterly, annually, that type of a thing, right, you have to plug in a number for n. Looking at number 17a, had to find the value or evaluate. So right here, I have, you can think in your head, e to the power of 3 log base e of 5. I'm just rewriting ln as log base e if that helps you. Notice that we can almost cancel these guys out here, but because of that 3 we can't. So what we have to do is we have to use the power property by putting that 3 up here. So what I really have is e to the log base e of 5 cubed, and then we're able to cancel out e and the natural logarithm, ln, giving us 5 cubed, which is really just 125. Looking at number 18, expanding the following. So I have log base fourth of this whole thing. There's 2 things inside, right? I'm multiplying 2 things. So the shortcut way of doing this is knowing that you're going to have 2 separate things at the end, square root of x plus log base 4 of y to the 4th. Anytime you have roots, you want to rewrite that in rational exponent form. So square root is the power of 1/2, cube root is the power of 1/3, and so forth. And then don't forget to move this power here out to the front. So your final answer is 1/2 log base 4 of x plus 4 log base 4 of y. For these expanding and condensing types of questions, remember if you have a positive out in front, that means you're going to be multiplying in the numerator. If you have a negative out in front, right, like this one here, then that means you are going to be dividing. It's going to go in the denominator. So looking at number 19, if I were a student doing this problem, I would do it as follows. Okay, I know I have a 2, an x, a y cube, and a z. So the 2 and the x are both in the numerator, so they're going to be ln of 2 plus ln of x, right, because they're both positive coefficients. And then I know that the y cube and the z, they're both in the denominator, so it's going to be negative out in front, so it's going to be negative ln of y cube minus ln of z. And then you move that 3 right out in front. Notice that the power of 3 only applies to the y, so just watch out for that type of a thing. Ln of 2 plus ln of x minus 3 ln of y minus ln of z is your final answer. Another way you can do this is by looking at just going in order. So I have a numerator over a denominator. Right? You can have ln of 2x minus ln of y cubed z, and then work from there. So right here, I can separate that as ln of 2 plus ln of x, since these are being multiplied. Right? And then right here, I have y cubed times z, so I can separate that. But notice that I'm subtracting the entire quantity, so it's minus ln of y cubed plus ln of z. And so because I'm subtracting the entire quantity, right, you would have to distribute that negative sign. So you end up with ln of 2 plus ln of x minus ln of y cubed minus ln of z. But remember, that power needs to be moved up to the front, and you will end up with this answer here. What is it? A 3 ln of y minus ln of z. Taking a look at number 21, you're condensing. For your final answer, you should have the log written out one time only, right? You're spelling out log one time only. So when I see the following, any powers, I'm going to move right? Any coefficients I move to the front, or to the power. So I have log base 6 of 4 squared plus log base 6 of x cubed minus log base 6 of 8. Okay. So anytime you have a positive out in front, it's going to be in the numerator being multiplied. Anytime you have a minus out in front, it's going to be dividing and be in the denominator of the argument. But we could also just go left or right, right? So if I do these, I'm adding, so 4 squared and x cubed are going to be multiplied on the inside. So that's log base 6. 4 squared is just 16, so that's 16 times x cubed. And I have minus log base 6 of 8. And again, going from left to right, now that I'm subtracting, the argument is now going to be divided on the inside. So I have log base 6 of 16x cubed divided by 8. And notice that 8 and 16 can simplify into log base 6 of 2x cubed. So you can put this parentheses here, although you wouldn't, it's not necessary to have your final answer. Log base 6 of 2x cubed is your final answer in condensed form. Number 24, when we're solving this, when you have an exponential equation, so you have like exponents here, you want to ask yourself, could I rewrite the bases of each side using the same base, right? So I have 6 here and I have 36 on the right hand side. So notice that the answer is yes, right? This is just 6 to the x plus 2. On the right hand, the 36 I could rewrite as 6 squared. So remember, you might have to rewrite the bases using like negative exponents. You might have to rewrite both sides of bases, like in terms of like 2 cubed, 2 to the 4th, that type of a thing, right, for other questions. So just keep an eye out for that. I have 6 to the something is equal to 6 to the something. So that means I can set the somethings equal to each other. So I have x plus 2 equal to 2 times the quantity 2x plus 3. So that's going to be 4x plus 6. When I solve for that, subtract x on both sides, subtract by 4. Get x is equal to negative 4/3. Number 25 has that asterisk. It's a calculator problem. So to solve this, whenever you have that exponential part, you want to get that by itself. So you add 3 on both sides. You get 4 to the x plus 1 equals 13. And right here, right, we're trying to undo the exponentiation. We're trying to bring down the x plus 1. So you have to take the log of both sides. And the base we're going to use is the base of whatever that exponent is on, so base 4. That allows us to cancel out the log base 4 and the 4. We get x plus 1 is equal to log base 4 of 13. Isolate x by subtracting 1 on both sides. So this is it, right? Because it's log base 4 of 13, then minus 1. So I should see that, but in your calculator, you would plug in log base 4 of 13 and then subtract 1. So rounding to 3 decimal places, you should get 0.850 as your final answer. Number 26, you have log base 2 of x plus log base 2 of x plus 6 equals 4. So when you have these log problems, you want to get a single log on either side, right? Or there should only be one log at most on each side. So right here on the left-hand side, I can condense this since they have the same base. And I'm adding, I could multiply the arguments. So I can condense this as a single log of log base 2 of x times x plus 6 is equal to 4. So here, now that I have a log equaling something, I can exponentiate both sides by base 2. That gives me x squared plus 6x is equal to 2 to the 4th, which gives me 16. Now I have a quadratic equation. I'm going to move everything over to one side. Factor. And so we get x equals negative 8 or x equals 2. Remember, when you have logarithmic equations, meaning you have a log in the original equation, you have to check your argument, right? The thing inside the log, the overall value must be positive. Otherwise, you have to toss it out because it's extraneous. So if I look at negative a, and if I plug it back in right here and here, do you see that how on the first one it already fails because log base 2 of negative 8 is negative, it's not positive, so that's out. If I plug in 2, right, if I plug in 2, log base 2 of 2, well, 2 is positive, and then right here 2 plus 6, right, is 8, and that's positive, so we're okay. We can keep the answer. So our final answer is just x equals positive 2. Number 27, you have common log of x minus 9 equals common log of 2x minus 11. Two ways to consider this. You can either see that you have a one-to-one property going on, like log of something equals log of something, therefore the two somethings must equal each other, or you can exponentiate by base 10 on both sides. So we get x minus 9 equals 2x minus 11. Subtract x on both sides, add 11 on both sides, and I get x equals 2. Again, because I have a log in the original equation, we plug it back in. So if I plug in 2, 2 minus 9 is negative. It's non-positive, therefore that does not work, and your final answer is no solution. There is no number x, right? There is no number such that when you plug it into x, that these would equal each other in a defined way, right? So no solution for 27. Looking at number 29, we have ln of x equals 2.536, and you are solving for the value of x. So if I want to get x by itself, I have to exponentiate both sides. Remember, ln is log base e, so I can exponentiate each side by e. These cancel out. I get x is equal to e to the 2.536. And when you put into your calculator, rounding to 3 decimal places, you get 12.629 as your final answer. Let's take a look at number 30 here. It says you put $5,000 in an account that yields 8.4 interest compounded monthly. So the keyword is compounded monthly. That's a clue that I will be using this formula here. Okay, so let's go and plug everything in. So you put in $5,000 and 8.4% interest, so 1, 2, that's going to be 0.084. For R, compounded monthly, so monthly is 12 times a year, so that's what's going to go right here. 12 again, and how much money will be in your account after 6 years. So you plug all of this into your calculator. I always just plug it all in one go, being careful that 12 times 6 that's one chunk in your exponent. Okay, so if you have an older version of a calculator, you might need to have an extra parentheses out here. So plug that into your calculator, rounding to the nearest cent, we get 8262.13. Number 31 says how much more money would be in your account if interest had been compounding continuously. So here's the keyword compounding continuously, means I will be using this formula here. Okay, again, this will be provided to you. You just need to know when to use what. So let's go ahead and plug in the values. I would have had, right, if I had $5,000, E, right, it's a button in your calculator that represents about 2.7. Rate is 0.084. T, right, still after 6 years. So again, 0.084 and 6, that product is in your exponent, so be careful of that. When I plug that into my calculator, I get $8,276.65. But the question asked you how much more money would you have had if you had it compounded continuously. So we have to do this value, right, 8276.65 minus the other value that we found on number 30, 8262.13, giving me a final answer of $14.52. So I would have $14.52 more in the account if the interest had been compounded continuously. Number 32, you find a rare stone on the lawn of C.C. Chess. When you take it to the Antiques Roadshow, the appraiser tells you that it is currently worth $32,000 and will appreciate, that means it'll go up, right, versus depreciate, which means the value will go down, 12% per year. How much will the stone be worth in 15 years? So when you have something that is increasing at the same percentage, per year or decreasing at the same percentage per year or per month or right on a regular basis, this is going to be an exponential equation. So remember, you're starting with 32,000. Don't forget that 1. It's appreciating, so it's going to be a plus. 12%, so we put that in terms of decimal form. And then we're going to have a t right here. So that's like our function. But we're trying to figure out how much it's going to be worth in 15 years. So instead of t, I'm going to plug in 15. Okay. Plug all of that into your calculator, right? Just all in one go. Make sure you have that parentheses here. Remember, technically this is equivalent to 1.12 if I were to add it. Doesn't matter in your calculator part, just plug all of that in or like so. And you get, is it $174,154.10 as your final answer. Number 33, your car is currently worth $28,000. It depreciates. That means it's going to go down in value at a rate of 17.5% per year. So again, do you see how it's a constant percent rate change? So it's going to be an exponential function. How much will it be worth in 3 years? So you set up a function. You start with $28,000, 1, right? And then you depreciate, so it's minus 17.5 in percent, right? That's going to be 0.175 to the t, right? The t could be the number of years, months, weeks, hours, any time period. But here it's going to be in years, and it's 3 years. So we're going to go ahead and plug in 3. So in our calculator, we plug in 28,000 times 1 minus 0.175 raised to the power of 3, which gives me a final value of $15,722.44. Number 34, it says you put $3,000 in a bank that earns 6.2% interest that is compounded continuously. So I know that I am using this formula here. After a certain number of years, you earned approximately $1,090 in interest. How many years did it take for you to earn that interest? Okay, so let's see what we know. It says that you put $3,000 in an account with 6.2% interest. 1, 2, so it's going to be 0.062. And then you would have your t here. Okay. After a certain number of years, so we're going to solve for t because it says after how many years, you earned approximately 1,090 in interest. Okay, so you have to be careful here. A is like the final amount you have. If we start with $3,000 and we earn this much in interest, our final amount is going to be 3,000 plus the interest, right? So 4,090 is going to be my A. So here's what I have, 0.062 t. Okay, so we want to figure out how many years it takes for me to earn that interest. Again, for A, it's not just the interest, it's the final amount, which is your initial amount, right, your principal, plus the interest. Okay, so we have an exponential equation here, and we need to solve this. So when you have an exponential equation, you always want to get that base and exponent part by itself. So in this case, since I'm multiplying by 3,000, we need to divide both sides by 3,000. So I get 4090 divided by 3,000 is equal to e to the 0.062t. And I'm trying to get t by itself, so I want to bring it down from the exponent. So to do that, I will need to take the natural log of both sides. I'm taking the natural log because remember, natural log is the same thing as log base e. This will allow me to cancel out the base of e, right? I can unexponentiate. So on the left hand side, I have the natural log of 4090 over 3,000. On the right hand side, I have 0.062t. And to get t by itself, I just need to divide by 0.062. And plugging this whole thing into your calculator. So it's the natural log of that, then divided by 0.062. T is going to be 4.998 ... Okay. I would tell you specifically what to round to, but in this case, you can just say it's about 5 years. So it would take about 5 years until you have an interest of $1,090. Again, pay attention to the directions. I might say round to the nearest hundredths, thousandths, tenth, that type of a thing. Number 35, it says in 1990 there were 33,500 farms in North Dakota. And then in 2000, so you'll notice that it's 10 years later, right? There were 30,800. Find the value of k for the exponential function, blah, blah, blah. So this is given to you, a formula, to model the number of farms. So this formula here is really, really similar to like the continuously compounding interest formula here. Okay, so this means the starting amount, this is your final amount. And then t is time, and then k is like some kind of constant. So let's go ahead and take a look at the following here. Let's go ahead and plug in what we know. So we have n is equal to, you started with 33,500. All right, that's your starting amount. And then you ended with, so for your final amount, we ended with right here, 30,800. 30,800. We know that the e goes right here, that's the base. It says, find the value of k, so k is your unknown, but we know that the t, time, is 10, right? Because it's 10 years has passed going from this many farms to that many farms, right? This is your initial amount, that's your final amount. Okay, so we have to solve for the value of k. Again, this is an exponential equation type of a question. I want to get the base raised to the power, this part by itself, and then I take the log of both sides and solve. So my first step would be to divide both sides by 33,500. Okay, so you can divide that. So I get 30,800 divided by 33,500 is equal to e to the k times 10, or I'll just read it as 10k. So how do I undo that exponentiation by base e? I take the ln of both sides. Again, ln is log base e. So these undo each other, canceling each other out. So I get 10k, right? 10k on the right-hand side. On the left-hand side, I have ln of 30,800 over 33,500. And to get k by itself, I would just divide by 10. So in your calculator, you will need to plug all of this in, and that would give us a k value of, let's see, so you can write that as your final answer, or you might have to give me everything, right? It's going to be like -0.0084030749, or I might ask you to round to a certain number of digits. For this particular problem, though, it's important that you keep a lot of the digits. So on the test, if I were to give you a problem like this, I would probably ask you to give me up to like 6 digits after the decimal or something like that. Okay, looking at B, it says use your model to predict the number of farms in North Dakota in 2010. So use your model to predict the number of farms in North Dakota in 2010. So to look at the following, right, we had this model here. We know that the final amount we're going to have is, we started with 33,500, and we know that the k value is that whole thing. Okay, so I'm going to plug that in. So 840300749. And for the t value, we started in 1990 and we're now at 2010. So the time that has elapsed is, right, what is that, 2010? That's going to be 20 years, so you put 20 there. Plug all of this into your calculator. So just type all of this in one go, and you would get about 28,317.6 ... So it would be about 28,317 farms. Again, I would tell you specifically what you would need to round to. Number 36 says the population of a small coastal resort town, currently 3,400, grows at a rate of 3% per year. So you're growing, so I know it's going to be plus. find the number of years it will take for the population to exceed 10,000. So I start with 3,400 and I'm growing at a rate of 1, 2, 3% per year. So let's find the number of years it will take for the population to exceed 10,000. So on the left hand side, I want my final value to be 10,000 or more than 10,000. So I'm solving this equation here. So let me go ahead and rewrite this so that the base is written as a single term 1.03. You didn't have to do that, but it just looks nicer if you do it this way. So again, I have an exponential equation. I'm trying to get the base raised to the power by itself. So that means I divide both sides by 3,400 first. So I get 10,000 divided by 3,400 is equal to 1.03 to the power of t. So how do I get t by itself? How do I get rid of that exponentiation? I take the log of both sides. And since the base 1.03 is what I'm trying to undo, I have to make the log base equal of 1.03. So these cancel out. I get t is equal to log base 1.03 of 10,000 over 3,400. Notice that if you wanted to, you could have cleaned that up as like 100 over 34, right? That's just a slightly reduced version. So plug this into your calculator and you get 36.497 ... So you need to have, right, about 37 years until you will exceed the population of 10,000. Number 37. On the Richter scale, the magnitude R of an earthquake of intensity I is given by this formula here. So R is the magnitude, where I is intensity, where I sub 0 is equal to 1, right, is the minimum intensity used for comparison. So that means for my formula here that's given to me, I really just have I over, right, I sub 0, or I sub naught is just 1, right? In other words, I have R equals the common log of I. That's my formula. Intensity is a measure of the wave energy of an earthquake. Find the magnitude R of an earthquake of intensity I equals 68,400,000. So I'm solving for R when I equals that. So all you have to do is just plug in the I. Plug that into your calculator. It's the common log of that, and you get like 7.835 ... Again, I would tell you what to round to, but it's about 7.8 in terms of the magnitude on the Richter scale. Taking a look at 41, when you're rounding to 3 decimal places or nearest thousands in your calculator, right, you can do math, alpha math, and just directly input log base 3 of 115. Or if you have an older version of a calculator where it hasn't been updated with this capability, you have to go a roundabout way. So you have to rewrite this as the common log of 115 divided by the common log of 3. So be careful that you're not doing the common log of 115 over 3, because it's not the same thing, right? So the common log of 115 divided by common log of 3, and that would give you the same answer as this guy here, and that's about 4.319.